This presentation covers VSEPR theory, which stands for valence shell electron pair repulsion, and also talks briefly about metallic bonding. VSEPR theory predicts the molecular shape of a bonded molecule. Basically what happens is the electrons around the central atom arrange themselves as far apart from each other as possible. They want as much of their own space as they can get. Unshared pairs of electrons, which we also call lone pairs, on the central atom are going to repel the most. So they need a little bit more space than electrons that are paired. So what you're doing when you use VSEPR theory to try to find the shape of a molecule is you're looking at what's connected to the central atom. The first shape we're going to look at is called linear. In linear, you have two atoms attached to a center atom. So you can see the center atom here in blue, and then it has these two red atoms that are attached. It doesn't have any lone pairs. The bond angle here, which is just showing you the angle between the central atom and the two atoms that are attached, that bond angle is 180 degrees, and an example is BEF2. So if we looked at this example over here, the two red ones would be F, and then the center blue one would be BE. So you'd have one BE and two Fs. The next shape we're going to talk about is trigonal planar. Trigonal planar now has three atoms attached to the central atom. So you still have the central atom here in blue, but now you have three atoms that are attached to it. Still have no lone pairs, and the bond angle this time is going to be 120 degrees. That angle is a little bit hard to see in the picture down here because you have to imagine this picture being three-dimensional. But if you can think of it, those three atoms that are attached are going to be as far apart from each other as possible. So a bond angle of 120 degrees gives them the most of their own space that they can get. So an example would be AlF3, and in that example, if we're using the one over here, the middle one would be the Al, and then these little red ones on the outside would be our three Fs to make AlF3. The next shape is tetrahedral. Tetrahedral still has the center atom, but now it has four atoms that are attached. So 1, 2, 3, 4 atoms attached to that central atom. There's still no lone pairs, and the bond angle this time is going to be 109.5 degrees. It's very exact. And again, that's because those four atoms want to have as much of their own space as possible and be as far apart from each other as they can be. So an example would be CH4, which is also known as methane. So in that case, C would be our center atom, and then all of these four outside atoms would be the H's, hydrogens. The last shape you need to know for this class is called bent. In bent, you have two atoms attached to a center atom. So here's our central atom, and now we have two that are attached. But unlike linear, we also have two lone pairs. So you can imagine the lone pairs over here on this side. So here's two little electrons, two lone pairs. So remember from the very beginning, we said lone pairs take up more space and they need more of their own room than electrons that are bonded. So the bond angle in a bent is going to be 104.5 degrees. And the reason why that angle is a little bit smaller than the one for tetrahedral that we looked at, where it had four things coming off the central atom, is because those lone pairs over there are actually going to be repelling a little bit more. So if you can think about it, this side is going to be taking up more space than this side over here that has the paired electrons and the atoms. So an example of this would be H2O. H2O is a bent molecule. I'm just going to redraw it since I made a mess on that other one. So you'd have one O and then two H's attached to it. And then there'd be lone pairs out here. All right, really quickly, we're going to talk a little bit about metallic bonding. So metallic bonds are formed between two or more metals. And the difference between ionic and covalent and metallic is in ionic, you are transferring electrons from one atom to another. In covalent, remember we said we're sharing those electrons. Well, in metallic bonding, you're not sharing or transferring, but the electrons are still kind of in there next to each other. So what happens in metallic bonding is the metal atoms form what we call lattices. And you may have heard that word before. Basically, it looks like this picture down here. You can kind of think of it like a fence or a grate of sorts. So we call that a lattice, that structure. And basically what's happening with the electrons is the outer valence shell electrons of each metal atom are contributing to what we call a sea of electrons in the lattice. So they're not really being shared, they're not really being transferred, they're just kind of hanging around, floating out there in the lattice. A couple properties of metallic bonds. They have high thermal, which means heat, and electrical conductivity. So that means that they're going to be really good at transferring heat and electricity. Wires are usually made out of metals. They're also malleable, which means that they can be hammered into sheets. And they're ductile, which means they can be drawn into a coil or a wire. And that concludes our very brief synopsis of VSEPR theory and metallic bonding.